Welcome to the part 2 of the Unit 4 Skeletal System screencast. In this screencast, we will identify the microscopic anatomical features of the long bone and explain the role of bone salts and the organic matrix in making bone both hard and flexible. In our last screencast, we examined the macroscopic features of a long bone. These are the features we could observe with our naked eye, for example, the diaphysis and the epiphyses. In this screencast, we will zoom in to the osseous tissue, specifically at the compact bone level, and identify the microscopic anatomical features that help explain how bone is built, destroyed, and why it's considered an organ. This diagram first shows where spongy, also known as cancellous bone, meets with dense bone right here at the edge of the proximal epiphysis. This cross section on top shows where the trabecula, which are the bars that cross the spaces and make up the characteristic honeycomb-like appearance of spongy bone, are located. Okay, so these are the trabecula. You can also notice the hyaline articular cartilage on top as well. It's right here, located here. And a blood vessel that snakes through the inside of compact bone. The blood vessel is indicative as well as of the nerves that also work through this trabecula. On the bottom right hand diagram, the focus is on the compact bone collar that surrounds the medullary cavity of this long bone. So we're zooming in right here. Notice that the blood vessel pokes out of a hole in a circular repeating structure called a Haversian system or osteon. These are the basic repeating units of bones, and it's the place where you're going to find cells that build, maintain, and destroy bones. Notice also the periosteum and another feature that we'll call the perforating or Sharpie's fibers. These are fibers that are made of collagen that pass through the periosteum and are attached to the outside of these osteons right here. Bone is made of repeating osteons, also known as Haversian systems. Each osteon itself has a central Haversian canal, and the canal is an opening in the center of the osteon that carries blood vessels and nerves. These entire systems are linked perpendicularly by Volkmann's canals. Bone itself is made of extracellular matrix of collagen and calcium salts, and each of these have a specific function that all add up to give bone its characteristic feel. Collagen gives resilience and strength, calcium and phosphorus salts give it its hardness, and fibers are built into the bone to give it even greater resiliency. So otherwise the bones become brittle, and you'll see this in people with osteoporosis, a condition referred to as brittle bone disease. So you can think of a bone like a city, made of different circular neighborhoods, like these osteons, and each neighborhood is fed by a major water or waste pipe, the Haversian canal. So these are right in the middle, and there's one right here as well. All these pipes connect to bigger pipes that go through, around, and through the city through the larger Volkmann's canals, which are found right here. In each neighborhood, you will find many houses or lacunae where special cells live. These cells are called osteocytes. Osteocytes have a branched look, and only one osteocyte lives in each lacuna, its own residence. The cells have to communicate with each other and exchange nutrients and waste, and tiny canals or little streets that connect that lacunae, called canaliculi, let this occur. So here's your singular canaliculus. So what are osteocytes doing hanging out in their lacunae? They first began their life as cells called osteoblasts. Osteoblasts are bone-building cells that secrete the matrix that makes up the bone. When osteoblasts become trapped in the matrix they're secreting, they stop building bone and start maintaining it. So their fate is to eventually turn into an osteocyte, living in a little lacunae. What's fascinating is that some of these osteocytes will live with you your whole life. An average lifespan for each of these little cells is about 50 years. When you get older, the rate of their death increases. So about 75% of the osteocytes are dead in 80-year-olds. And their death is associated to a programmed self-suicide called apoptosis. This is one of the reasons that osteoporosis is prevalent in older people. One thing to also note is that the matrix being secreted forms in concentric circles. So these are circles within circles, and you can see the repeating pattern here. These rings are called lamellae. Here's a nice cross-section of a neighborhood. Looks kind of like a pie slice, where you see, you can't see them in here, but these osteocytes, star-branched, are housed in the lacunae, and they secrete the matrix that forms the lamellae. Bone salts are deposited by osteoblasts, and osteoblasts also form a matrix in a process called ossification. This is where the hardening of bone occurs from cartilage. There's two types of ossification: intramembranous, where bone replaces fibers or fibrous connective tissue, for example, in the flat bone of the skull, and endochondral ossification. And this is the one that you're probably most familiar with, where bone replaces cartilage, a cartilage model. Most bones do form this way. So, for example, a fetus developing will have a cartilage model first, and also day-to-day growth and repair from any kind of injury. So broken bone will also form a cartilage model first, and endochondral ossification will occur so you can have that broken bone, so that broken bone can be replaced. There are several different types of cells involved in all this reshaping of bone. Osteoblasts are the bone building cells. They secrete fibers, and promote deposition of calcium salts and fibers in that matrix. Osteoclasts are bone absorbing cells, so they crunch and they remove bone and break it down, and they assist in the returning of calcium and phosphate back into the bloodstream. Osteocytes are just mature bone cells that are part of the regular maintenance of bone. And chondrocytes, which I haven't talked about, are associated with cartilage formation. The process of ossification, especially the intramembranous and endochondral ossification, will be addressed in the next screencast.